Hi, everyone. So we are going to start our afternoon session. I'm Liu, and today is very special because our first speaker in the afternoon session, our very great and very kind Ziming, to talk about the very latest work on CANs, which is a very amazing work. So Ziming is a PhD student at MIT Physics, working with my STEMA. So let's listen to Ziming's talk.
Yeah, thank you so much, Dee, for the introduction. I'm Ziming. I'm happy to present our recent work, Kolmogorov-Arnold Networks. So today's AI is built upon this math theorem called the universal approximation theorem, which tells you can decompose a high-dimensional function into a linear combination of some random features constructed from some nonlinear function sigma here. It's equivalent to this two-layer network. And of course, you can generalize this to deeper layers. So people have called it the multi-layer perceptrons. Did you want to start that? Yeah, and the foundation. and in this talk, we'll see an alternative math theorem called, namely, the Kolmogorov-Arnold representation theorem, and how we can build a whole different AI world. Well, maybe something similar based on this Kolmogorov-Arnold representation theorem. So first, just some boring stuff taken from Wikipedia. The representation theorem says that if f is a multivariate continuous function, then it can be written as a finite composition of continuous functions of a single variable and binary operation of addition. So we have this quite scary representation here, but don't worry about it. I will show that very intuitively we can draw a diagram for it. In a sense, the theorem shows that the only true multivariate function is the sum, since every other function can be written using univariate functions and summing. So this sounds really great news. By the way, they call this capital phi q alpha functions and this phi qp as inner functions, which we will refer to later. So that sounds really great news because we can decompose a high-dimensional function into a bunch of one-dimensional functions which no longer have curse of dimensionalities. So can we say the curse of dimensionality is gone? And the dream was broken by this old paper back in 1989. Jarossi and Paggio, in their paper, they comment that we review Kolmogorov's theorem in terms of simple functions of we review Kolmogorov's theorem on the representation of functions of several variables in terms of functions of one variable and show that it is irrelevant in the context of networks for learning. So that sounds really sad. Is that the end of the story? Is that the last nail to the coffin? And that's the end of my talk. Thank you for attention. We can probably just pack and go home. I'm just kidding. So what's going wrong here? The key here is smoothness. So the theorem tells us you can decompose a continuous function into 1D continuous functions. But those 1D continuous functions are not guaranteed to be smooth. But in practice, what we care about and what neural networks are able to parameterize are smooth functions in order for gradient descent to work. So their attacking point is basically that the theorem fails to be true if the inner functions are required to be smooth. Hence, their conclusion is a stable and usable exact representation of a function in terms of two or more layer networks seems hopeless. So note the wording here, it seems hopeless. No one has ever viewed it and showed it doesn't perform, it just seems hopeless in a mathematical sense. So again, although it seems hopeless from the mathematical perspective, we're physicists, and we're proud that our level of rigor is lower than mathematicians. Well, I shouldn't speak for others, but at least for myself. So I tend to have this naive optimism. So first, empirically, sometimes we don't care about exact representations. Maybe approximate ones may suffice. And secondly, a common wisdom of modern deep learning is just going deeper without worrying about other things. You just first stack more layers, and this will give you more expressive power. So that's the belief. Lastly, just the can-do spirit. Let's just do it and see how it works in practice. It may not work, it may work, but at least we should first try it and before we came to a conclusion. Just to properly set the expectation here, the chance may not work properly for the worst cases. Because for mathematicians and computer scientists, theoretical computer scientists, they care a lot about worst cases analysis. But in many cases in physics, we care about typical cases. So with the can-do spirit, me and my awesome collaborators shown here extend beyond the Kolmogorov representation to deeper representations and propose this new architecture called CAN, Kolmogorov-Arnold Networks. So I will annoy you again. First, here's the outline of the talk. I will first annoy you again with some more math stuff, and then I will cover two aspects of CANs for it being accurate and for it being interpretable. And in the end, I will try to quickly advertise for work in progress, CAN 2.0, where we attempt to better synergize the world of science and CANs, or machine learning in general. So first, the math foundation. So the representation in the original theorems looks quite scary. It has this, double summation and also this outer function, inner functions look quite scary. But remember, these functions are only one-dimensional. So you can easily place them on this diagram, and inner functions, they naturally go into the first layer of the network, and outer functions go into the second layer of the network, and you have the summation operation on nodes. So that's basically the network is the exact correspondence with this representation written in mathematical expression. So to make things even more intuitive, because these 1D functions are 1D, we can choose these 1D curves so that you can very intuitively understand what each function is activating, how they're working. And this is a CAN diagram we will encounter again and again in this talk. So after we drew this representation as this two-layer network, it becomes quite natural regarding how to extend it to deeper networks. But just to make it sound less trivial, so that you trust me that we have more contribution than just stacking more layers, I will share one failed attempt at first. So if you abstract away the representation by just focusing on the indices, you realize that the outer function have only one index and the inner function have two indices. So a natural extension is just by counting 1, 2, 3, 4. So you may imagine by stacking, by building a 3-layer CAN, you need 3 indices for the, say, inner layer, and you even need 4 indices for the inner layer. But that's hopeless unscalable because now we have this exponential growth, because when we have n layers, the number of functions required for the most inner layer is, say, 10 to the power of n, which is exponential. So hopeless to scale. Actually, that failed idea stuck with us for a while before we came up with the correct one. So we noticed that although the outer functions only have one explicit index, it actually has one dummy index because f here is a scalar function. So actually, it has a dummy index which is 1. And now both the outer and inner functions have 2 indices, so we can easily define the CAN layer as having 2 indices. And with that, you can easily stack more and more layers as a chain by just contracting the nearby, like the same indices as in Einstein summation. So that's great news because now all the layers have just 2 indices. We no longer have the scalability problem. Just to make it more explicit, for the first layer we have Q. We have the index P in the first layer, Q in the output, and in the second layer we have Q in the input and 1 in the output. And to be clear, this two-layer CAN, although the terminology CAN is new, people call this Kolmogorov network before, intentionally or unintentionally leaving Arnold out of this name. But we want to bring Arnold back and also make the network deeper. So by having the CAN layer as the building block, we have the original Kolmogorov network, which is a two-layer CAN, but we can also make it 3-layer, 4-layer, 5-layer, as deep as we want, just like how you stack a neural net MLP to become deeper and deeper. So an immediate question is, why do we need deep neural networks? As I said, deep CANs have more expressive power. Let's suppose we try to fix this function. If you do the construction, you realize that you would need at least 3 layers of nonlinear functions. We need the squared function, we need the sine, we need the exponential, and this corresponds to this. It's a video. You can see throughout training, this is a 3-layer CAN. These activation functions starting from random, but gradually evolve to be quadratic, to be sine, to be exponential, which is exactly what we would expect from the tree expression, the tree structure of this expression. So I have just sketched out the skeleton of the CAN network. Now we also want to fill in the details by specifying how we actually parameterize these 1D functions. So we use the B-spline functions. So for B-spline functions, it's basically that we first have some local B-spline bases. They're localized piecewise polynomials, which have compact support, which means that it actually should be 0 outside the domain. But we have many copies of this B-spline basis all over the place, and the function is parameterized as a linear combination of these B-spline bases. Because it's all the operation here is differentiable, so we can just leverage backpropagation to obtain a gradient and use the standard way to train the CAN network. So I've been presenting CANs as something completely different from MLP, but it's interesting to note, actually, in some sense, MLPs and CAN are dual, in the sense that in MLPs, they have fixed activation functions on nodes, learnable weights on edges, while in CANs, they have learnable activation functions on edges, while have no learnable parameters on nodes. It's also nodes is basically summing up everything that's coming in. So the first aspect that I would to mention about CAN is accuracy. So I will analyze this accuracy from the perspective of scaling laws. So the theorem, the original theorem, boils down to, well, roughly it boils down to the simple equality, which is an n-dimensional function is equivalent. Well, by equivalent, it's in the rough sense, but it's roughly equivalent to a polynomial number of n of one-dimensional functions. It's specified by the original Kolmogorov theorem. If we have n inputs and on the order of n hidden neurons and have some constant number of layers, then we only need some polynomial number of 1D functions. So if we recall the classical approximation theory, if we want to approximate an n-dimensional function, and the way we do it is by having a uniform grids in this d-dimensional hypercube. The most vanilla method, but just to get the sense of this of the order. So in this case, if we have say 10 points along each dimension, then we would need 10 to the n number of points altogether because it's an n-dimensional function. And if we're using k-spline basis to approximate the function, then the approximation error would scale as a power law against the number of parameters, and the scaling exponent is k+1 over n. So it's disastrous. It's known as the curse of dimensionality because of this 1/n phenomenon. When you have a very large n, this scaling exponent decays really fast. Decays really slow. But for an n-dimensional function, if the n-dimensional function can be decomposable into Kolmogorov-Arnold representation, then all we need to learn is this one-dimensional functions. So effectively now, small n effectively becomes 1. But notice that now instead of having one function to approximate, we have polynomial of n number of 1D functions to approximate. But that's fine because that only come into this constant factor. It doesn't affect the scaling law here. So still it still speeds up the scaling law to a great extent, at least theoretically. So I will first show some empirical results. It's really simple examples, but just to show that it does not only exist in theory, but can exist in practice. So here we examine some symbolic formulas. Well, you can say we cheated a little bit because we know these formulas have exact Kolmogorov representation. We know that for sure because we can write it down, the decomposition. But notice that this symbolic formulas is a 1D, 2D, 2D, 4D, and even 100D. And the red dashed line are for the theoretical prediction, which is n to the power of n to the minus 4. And the blue lines correspond to the CAN performance, which agree quite well with the theoretical prediction. Well, you can say it starts to fail for high dimensions, but it's already 100 dimensions, and there's some and the data is not too much in this test. So one can in principle further increase the performance by adding more data. But I want to point to the fact that if you look at those colorful curves, they correspond to MLPs of different layers, and you would clearly see that. For MLPs, you first goes down, the loss first goes down, but then levels off really quickly. So good news is that we seem to have avoided curse of dimensionality on these simple cases and beat beyond the scaling laws that MLPs have. That's good news. But again, with caveats. So the 1989 paper has made some valuable points. So first, there might not exist finite smooth Kolmogorov-Arnold representations. As that paper argued, you can decompose it into finite continuous representation, but not necessarily finite smooth representations. So this might even be, their claim could also apply to even deeper representations, although we are, we're extending to deeper, but it may still apply. Although by stacking more and more layers, our expressive power has grown to a great extent. So the problem is alleviated, but not fully solved. And the second part is regarding learnability, the training algorithm. Even if these exact representations exist, our learning algorithms may not find these solutions due to whatever optimization error or some other stuff. CAN is like a function approximator, just like MLPs, and people have played around in all different contexts. And here we can do the same thing for physics-informed neural networks, where people use the MLP to parameterize solutions to partial differential equations. So in the context of physics-informed learning, in the neural network, we see that by using grid extension, we can achieve better performance than MLPs on this simple photon problem. And there are a bunch of works following our work on PDE solving. There are two nice papers from Professor George Kaniadakis' group and one paper from Tsinghua group. And they have some quite interesting takeaways. So the first takeaway is that PyCAN, the package we released, is extremely easy to train. Use efficient CAN instead, which is the repo that came just 2 days after we after we released the PyCam package. It's fair to say, because at that time, we were not even supporting GPU at that time. We have the symbolic branch, which allows you to do some iteration, which is not GPU friendly. So it's fair. And the second takeaway, Chebyshev cans, which basically you still have cans, but you replace the B-splines with Chebyshev polynomials. The Chebyshev cans can beat MLPs, but B-spline-based cans cannot beat MLPs. And then takeaway number 3, which is kind of contradicting takeaway number 2, is that B-spline-based cans, which is what we propose, with B-spline-based cans are awesome, beating MLPs, except for just one case in the paper, which is the irregular domain case. So there seems a lot of subtlety here. So the last takeaway is don't trust any takeaway that I've spoken like including what I said and what other people said. At this point, it's still too early to draw any universal conclusion. So try for yourself on your problem. The conclusion, your experience, may strongly depend on the exact problem that you are attacking. But maybe just say a little bit more on in our defense. So development takes time, and MLP is kind of like a mature person, while I'm kind of still like a baby. So there are more development to be on the road. In the second part, I want to talk about the interpretability of cans, making it a suitable tool for scientific discoveries. One kind of problems in machine learning is supervised learning, where you have some input x1 to xn, and you have output y, and you want to figure out the mapping from this input and output. And ideally, you want to understand, ideally the symbolic formula of this mapping. And here we show some examples. That the can is sees the data, takes in the data x and y, and want to predict x multiplies y. Upon first inspection, it looks really weird. What's the internal computation can is doing here? But after you stare at it for a while, you realize that it discovers something really smart, which basically leveraging the quadratic function here. And also when the can tries to do division, it rediscovers its logarithm trick. Like you first take the logarithm and then subtract the two numbers and then take the exponential back. Another example I want to highlight is that it can learn something even though suppose you don't know about the Bessel function, but it can, because it's parameterized at B-splines, it can learn the function anyway. Then maybe you go to experts, the expert will tell you that, oh, it's a Bessel function. Another kind of problems in machine learning is unsupervised learning. I probably don't have time to dive deep into this, but you take my words that we managed, like in the paper, we use contrastive learning to convert unsupervised learning to supervised learning problems. So, and we already have tools for supervised learning, so that's solved. One very controversial paragraph we had in the paper, which has been criticized a lot on social media, is that we said cans as a language model for AI plus science. And the logic is the reason why large language models are so transformative is because they are useful to anyone who can speak natural language. But language of science is functions. Because cans are composed of one-dimensional functions, which are somehow interpretable, you can say. So when a human user stares at a can, it's like communicating with it using the language of functions. So just to give one example, so here is an imaginary conversation between my advisor, Max. Max is not here, right? Okay. So imaginary conversation between my advisor, Max, with Ken. So here I illustrate Ken as this trisolarian from the three-body problem, because the trisolarians, their brains are totally transparent and they cannot hide any secret from other people, from other trisolarians. This is exactly the case of Ken, where we can really stare at the Ken diagram and understand what's happened there. So Max went up and say, here's my data set. It contains the mystery of our universe, and I want you to figure it out. And Ken's like, I'm ready, Max. Here's my brain, initialized like this. Great, train your brain. And after training, you got this nice compact subnetwork. But Max is not satisfied with that. He further insists that we should prune it down. And after pruning, we got this really small, compact subnetwork. And further, Max asked for symbolify this network. And yeah, and Ken's like, yes, I can. And I finally got this symbolic formula, which is quite interpretable. Yeah, let's imagine another conversation Max would have with MLP. So Max had the same opening line. Here's my data set. I want you to figure out the puzzle of the universe, and MLP initializes its brain like this. And then after training, the brain remains like very not interpretable. So Max now got confused. Did you really train it? It looks as messy as before. And MLP is like, I really trained it. The loss is pretty low. What's really going on? And MLP says that you stupid humans just cannot understand how I do the computation. So I not only want to show this rather contrived conversation Max had with this alien guys on this contrived example, I want to show that this can be useful on Earth and for everyday scientific research. So yeah, so in the paper, we show two examples. The first example is the knot theory, thanks to Fabian and Jim, who point me to this example. It's in DeepMind's Nature paper published 3 years ago. They train an MLP and they use attribution methods to identify important relevant variables. So the problem setup is that you have knot, and each knot is associated with some topological invariance, and we want to figure out the relations between this topological invariance. And in their supervised setup, they take in some invariance and want to predict the invariance called the signature. So they train MLP, use attribution, figure out relevant variables, and then their human scientists come up with this slope concept based on this, relevant variables, and then the human scientists prove it to be correct. So we ask this question: can we rediscover this result with Kant, with more automation, and perhaps discover something even new? So first, we can rediscover the relevant variables with a much smaller Kant. Notice that we can literally visualize the head, like the brain of the Kant here. We only have one hidden neuron here, one hidden layer, one hidden neuron. And it can already achieve like around 80% accuracy, which is also something similar reported in the DeepMind paper. But they have a 5-layer MLP with 300 neurons in each hidden layer. That's amounting to around million, on the order of million parameters. And we can also symbolify like the first line here is what the DeepMind human scientists discovered. And we can rediscover it. It's something close to it, but not exact. With some inductive biases, that's something we need. That's something we need to confess. But without inductive biases, we also find some other formulas which might be interesting, which might not. But still, anyway, it can provide some symbolic hypothesis. Another thing that I find quite interesting is that for knot theory in the unsupervised learning setup, where we don't need to manually partition variables into input and output variables, we find that there are 3 relations. Like we automatically find there are 3 relations. One relation is the relation presented in the previous one, supervised learning task, but we have 2 other relations, which is also quite interesting. But to our disappointment or to our satisfaction, this is something known in the literature. So we are not discovering some groundbreaking math here, but it's satisfactory that our discovery makes sense. So we also applied CAM to this physics example, namely Anderson localization. So I probably don't have time. This is in collaboration with Marin's group. I probably don't have time to go into the details, but the takeaway here is, again, you can use an extremely small CAM, which is extremely interpretable for this task. So in the last section, I want to mention just a little bit about our work in progress, CAM 2.0. Hopefully it will post it to our site soon. So the goal for CAN 2.0 is to synergize science and CANs more seamlessly. I believe Professor Maxwell in his talk yesterday, he mentioned that we eagerly need symbolic AI. This is because science relies a lot on symbolism. We write down symbolic equations, do symbolic manipulations, but neural networks is most basically on connectionism. So there is this incompatibility between science and neural networks in general. And deep learning has been termed as software 2.0 by Andrew Karpathy. The reason why it's called software 2.0 is to show that it's more advanced than traditional software in the sense that you can learn new things from data, but it's still less, but it still has something, have cons, say they're less interpretable or controllable compared to software 1.0. So in the best world, we want to combine both. And here I want to temporarily make this bold claim that CAN is a combination, or it can be, it's a quantum superposition of software 1.0 and 2.0 at the same time. And the reason for that is that if you take a symbolic formula, you can, we now have a compiler which allows you to compile symbolic formula into this CAN network. You may notice that we have some extra multiplication symbols. That's another thing we have updated because multiplication is so natural in science. And what we have done before is that we have this and then we try to decompile it into the formula, but now we can go both ways. The scalability, but my bold claim of course, came with some caveats. So the claim strongly depends on the scalability of your problem scale and also the levels of interpretability. Imagine you can gain symbolic interpretation for some small scale CAN networks, but when you have more and more layers, it soon becomes uncontrollable, unmanageable for larger scales. And also for levels of interpretability, we mainly focused on the symbolic interpretation, converting these networks into symbolic formulas, but there are also other levels of interpretability which are sort of more coarse-grained, but could also be informative, like the module on the level of modularity, or simply understand the importance of features. So by different levels of interpretability, we may sweep a free to frontier in this space. So the takeaway is basically that if we want to generalize the interpretability of the CAN network to larger scales, maybe we should be be less ambitious about always extracting the symbolic formulas out of it, but sometimes be satisfied with extracting the module structure or feature and importance. So this is a teaser figure for CAN 2.0, where, as I said, we studied 3 levels of interpretability, including important features, modular structures, symbolic formulas, and in both ways. You can both incorporate scientific knowledge into CAN, or you can also extract scientific insights from CANs. Just before I close, I'm running out of time, but just before I close, I want to bring up this philosophical comment. So CAN and MLP, so for CANs, the parts are complex, like this one-dimensional functions. They can be any function, sine, exponential, can be very complex, but the way to combine them are simple, or hopefully to be simple. Like after training, we hope the computation graph are sparse. So this is a little bit aligned with reductionism. Well, for MLPs, the parts are simple, but the combinations are complex, which is we sort of hope the complexity comes from the emergence of the complicated connecting patterns, which is sort of kind of aligned with holism. So by analogy, CAN is like a clock. The pieces in the clock are customized and have clear purposes. It's easy to tear them apart and reassemble, but it takes craftsmanship to build these pieces. But for MLPs, it's like a house made of bricks. The pieces are produced in simple, standard ways, but once the house is built, it's hard to tear them apart and reassemble. So with that, that really, that is the real end of this talk. And I welcome you to try by simply typing in Pippin slow PyCAN in your terminal. And yeah, with that, thanks so much for your attention, and happy to take questions.
Yeah, thanks to me for the excellent and a very inspiring talk. So it's time for questions, especially you can ask some secret if I can in this variable scenario. Yes.
Very nice talk. I'm excited. However, I want to contradict you in one thing, and that is, I come from perturbable QCD, and interpretable formulas to us, I mean, they have like, millions of lines, and I think we have tossed that out the window while trying to gain precision. And this is where my question comes. Do you have like some kind of, and sorry, I didn't read your paper. Do you have a study where you actually check the scaling, like improved scaling, or when you go to like higher dimensions in some kind of task where you actually see if that the promise improved scaling actually works on for what kind of classes of functions?
Yeah, that's a great question. Yeah, I mean, we only tried for no like fewer than 10 variables and no more than 10 terms in the yeah, but that's definitely an interesting direction. We'll definitely test it.
So what happened until 10, up to 10, what happened? Does it scale?
We haven't tested yet.
Thank you very much for the great talk. I have a question, actually. It seems like the exponential function does the trick in many, many places in physics, because if you think about the Gabor cluster ansatz, you start from some simple linear operator, then you exponentiate it, and from the sum, you get the product. And here it seems like it is often the case, right? Because if you have the sum of two functions, then you exponentiate it, you get the product, so you get correlations.
Yes.
But then at some point, you show that now you're introducing the multiplication symbol, not just the sum. And I was wondering, would you gain a lot by using complex parameters? Because in that case, if you do the product, when you use the exponential, it's always positive, the product, right? I mean, because if you use real numbers, the exponential of x plus y is always positive. But now if x and y are complex, then you get a phase.
That's the way
you would get. And we typically use complex networks in neural quantum states that are more expressive. And I was wondering if you could comment on that, and then the importance of locality, because splines are local, whereas Chebyshev polynomials are not. So how important really is using splines versus a basis for the one-dimensional functions?
Yeah, thanks for the great question. So the first question is about sorry, I'll first answer the second question. So for Chebyshev and B splines, I guess it highly depends on the kind of problems you're addressing. If it's high frequency, if it has some weird local structure, like you have some high frequency nodes locally, then maybe B splines are acting better. We also have a follow-up work showing that if you start from like very fine-grained B spline grids, you may get into problems. So you may want to start from something smoother and then try to gradually have more finer grids. And regarding the first question, it's really interesting to think about how to generalize this to complex numbers. Yeah, to be honest, I'm not very familiar with the context of the quantum neural state and how complex numbers are computed inside neural networks. But like our first step is dealing with real numbers because they are much more tools for real number neural networks. I guess I'm not in my place. I guess you are better in the place to comment like how hard how technical the challenge is to deal with complex numbers in neural networks. And yeah, we can check more offline if you have any insight on how to make it complex. Thank you.
Great talk to me. So I have like a follow-up question for the previous one. So could you comment on like the finite approximation error in relation to the complexity of the function here? Right. So I guess at a high level, you're using different spline functions to do interpolation of the data, and there are many choices, of course, for the functions that you're using. Intuitively, I guess, the more complex expressive the function is, then the better approximation power is. And is there like a analytical relationship about that? Like a second question is like in this design, because when you mute the index, you're essentially tying the nodes. What if you don't do that? What if you allow split the nodes and it doesn't scale, of course, but in terms of expressivity of your network, how would it change it?
Regarding the first question, I haven't tried it myself, but for the paper from the Tsinghua University, they showed that the relation between the B-spline based Kolmogorov networks with finite basis, with finite element method, something like that. And I guess yeah, to be honest, it's something to be thinking about. I haven't really think much about that. And regarding the second question, are you saying that we need to first guess the structure of the can, so to make sure it matched the inductive bias?
Like when you tie the node, because when you put the original layer in the 3-layer case, right?
Yes.
You mute one of the index because you're tying the nodes. So like one node actually have 2 incoming edges are shared in the middle layer, So therefore you can actually.
You mean this one?
Yeah, like for example, in the middle node, it's actually have 2 incoming edges, right, from bottom to top, and implicitly you're assuming that that's actually it's like shared in the sum. What if you split that node with different functions?
So what do you mean by split?
Like basically don't mute the index.
Don't mute the index. So the general strategy, sorry, I'm not sure if I fully understand the question, but the general strategy is we first take a large enough fully connected neural CAN network. And then in training, like we have no assumption, we just use training, we just use regularization to learn something parsimonious. I guess
like their assumption about certain groups of functions have to be the same as the other group of functions.
Oh, I see your point. Yeah, no. So I guess there's no such assumptions. Like all of them are not locked. Although in the first version of the Python package we have a cute functionality called lock, where allow you to lock some of functions to be the same for some equivariant purposes. Like when you want to impose equivariance, sometimes you need some functions to share the weights.
Okay, well, maybe one last question.
Thank you, Ziming. Can you comment on the ability of cans to overfit? So, I mean, I can imagine if I just, as a toy example, have some noisy linear data, I could see maybe a failure mode if you have an over-parameterized can, it's just a bunch of sinusoids and exponentials maybe to fit all that instead of the line.
Yeah, that's a great question. So we have follow-up work on the spectral bias of cans compared to MLPs. So it's known that MLPs have spectral bias towards learning low frequency modes at least first, and then gradually learn high frequency. But CAN does not have this strong structural bias. It learns low frequency and high frequency at the same time. So it's it's a feature and a bug. You can say it's a feature because if your goal is a high dimensional function, then it's a feature for you. If you are learning something smooth and your high frequency components are those noise, then it's a bug. So yeah, but I guess it's not like a deal breaker. You can say you can still like add regularizations where you start from a smooth CAN first and you gradually extend your grids to make it more expressive until you see at one point that the test law starts to go up. You know that, oh, it starts to underfitting. Maybe I should stop here.
Thank you. Yeah, that's great.
Okay, yeah, thanks for the discussion, and thanks Ziming again for the nice talk.